Hello everyone. In the last lecture, I asked you if you will be given an initial value problem and asked whether the solution of that initial value problem exists or not. And if exists, then it is unique or you can find out some other solutions. Then what will you do? So for that, today we are starting this existence and uniqueness theorem, which is also known as Picard's theorem. So this theorem will help us in knowing that the solution of our initial value problem exists or not, or if it exists, then is it unique or not, right? So this theorem says that if you are given an initial value problem, y prime equals fxy with an initial condition yx not equals y naught, and the function this function fxy and its derivative, partial derivative with respect to y, these both functions comes out to be continuous in some open rectangle R equals xy, a where x is less than a and x is greater than a and less than b, and y is greater than c and less than d. Okay, and this R contains the point x naught y naught, then the initial value problem will have a unique solution in some closed interval I given by x naught minus h to x naught plus h, where h is greater than 0. Now it must be a bit difficult for you to understand this definition, right? So I'll try explaining this to you graphically. So here you can see that this is our fxy. Okay, this fxy. The initial value problem was given, right? As y prime equals fxy. So we are plotting this fxy. Okay, and we will try to know about the behavior of this fxy in the region R1. Okay, now what is this region R1? Here in the definition, you can see that R1 is a region containing all the points of type x comma y in which x lies between a and b and y lies between c and d. Right? It is an open rectangle. Here you can see this rectangle, okay, R1. So this is the region, and we have to find out that if this function and its partial derivative with respect to y, these two functions are continuous in this open rectangle or not. Now, how will you come to know that we have to check the behavior of fxy and its partial derivative with respect to y in this region only? How will you come to know the region R1, where it lies? Okay, so the condition is R1 should contain the point x naught, y naught. And what is this point x naught, y naught? This is nothing but our initial condition. Okay, what was our initial condition? That at x naught our y will become y naught. So this x naught, y naught is our initial condition. This is the point that depicts our initial condition. Now we have this region R1, okay, and this region contains our point x naught, y naught, and you know that the function fxy is continuous. You can see the curve, okay, it do not have any sharp point or it does not breaks anywhere, right? So it is continuous in this region, and if you calculate its partial derivative and it also comes out to be continuous in this region, then what we'll have is, then we can say that our initial value problem, this initial value problem will have a unique solution in this interval. Okay, in this interval. Now this interval is x naught minus h, x naught plus h. Why? Because this point you can know, you know that it is x naught, right? Here you can see that it is x naught, y naught. So here this will be x naught. Okay, now if I take a distance of h on the left side, so this point will become x naught minus h, and if I take the same distance at the right side, then this point will become x naught plus h. So this interval will be from x naught minus h to x naught plus h. Okay, so what we'll have is, we can say that our initial problem will have a unique solution in this closed interval I equals to x naught minus h to x naught plus h. Now again I'm repeating, if you are given an initial value problem and an initial condition with it, and you find out that the function fxy and its partial derivative with respect to y are continuous in some open rectangle R1. Okay, this open rectangle that contains all the points of type x comma y, where x lies between a and b and y lies between c and d. Okay, and this region should also contain x naught y naught. Okay, and this x naught y naught we are getting from the initial condition. Okay, so if these two functions are continuous in this region, then we can say that our initial value problem will have a unique solution in the closed interval I equals x naught minus h to x naught plus h. Okay, now we have a question. An example, consider an IVP, an initial value problem, dy by dx equals x. Okay, and the initial condition is given as y at x equal to 0 is 1. Okay, so this is our x naught and this is our y naught. Now you can see that this is our fxy, right? Our initial value problem was type of y prime equals fxy. So this is our fxy, and you know that this x is a polynomial function and it will be continuous for all x and y, right? Also, the partial derivative of this with respect to y. Now, if I try finding out the partial derivative of x with respect to y, this will become constant. Okay, and the derivative of a constant comes out to be 0. Okay, so the partial derivative of fxy with respect to y will come out to be 0, which is a constant function, right? And that will also be continuous for all x and y's, right? So we know that the fxy itself and its derivative both are continuous everywhere. That means, using existence and uniqueness theorem, we can say that, or we can conclude that the initial value problem that is given to us, that initial value problem will have a unique solution. Okay. Now, sometimes we come across some functions that lack the continuous partial derivative. For example, if you are given an initial value problem of type this, dy by dx equals root y, then you know that this will be your fxy, right? And if you try finding out the partial derivative of this function with respect to y, you'll get 1 over 2 root y, that you know will not be continuous at y equal to 0. Okay, so what do we do in that case? So that will continue in our next lecture. That's all for today. Thanks for watching.